Okay, so let's continue. Okay, so we say once we have this cut point, let's say once we have this cut point L, then we can check whether this decision making rule is good. We can find this alpha. And on the other hand, if we want to guarantee this alpha, then we can determine the cutoff point. Let's check this problem. Like some people claim GPA for all at least 3.00 with standard deviation thus. So this claims mu equals 3.00 with sigma is 0.3. So we want to test their claim. So we will check some people. So let's say we will check 16 students. Okay, then we want to find, let's say we want to make a decision making rule. So here is 3.00. So we say GPA is high is good. So in this part, we will accept. We say, oh, GPA is good. So if average samples average too low, like we put the cut point as 2.2, we put as cut point as L. So this, if here we say low. So if larger than this cut point L, we believe the GPA is good, or we will accept their claim, right? So our question is, what is the L? What is L? What is this cut point? If we want to guarantee the alpha is 0.05, or use this cut point to make a decision, our mistake, the chance of our mistake is at most 5%. We want to guarantee this. So such a problem means like we know alpha, we want to find a cut point. So we know 0.05 is alpha, so alpha is top 1 error. So top 1 error is reject HO or refuse HO when HO is true. So when we will reject HO, we say when X bar is less than L. So when HO is true, when mu equals 3.00. So, okay, so when mu equals 3.00, then we can know the distribution for X bar, right? X bar follow this normal, just the mu is so say mu is 3.00, and sigma, so sigma of radical n, sigma is 0.3, n we determine like n is 16. Okay, so X bar follow this normal. So here a little bit calculation, we find this is 0.0075, right? Radical 3 over 4. So we have this X bar follow this normal. So then we want to find a cut point such that X bar less than this L is 0.05. So how can we find this L? So we say at the first we just changing this to standard normal, right? Changing this X bar this to Z. So Z less than minus mu divided by sigma. So this number, so by now this is follow standard normal. So we can check standard normal, right? So we want to find this cut point such that this is 0.05. Less than this cut point, this is 0.05. So from the, so we need to determine this cut point from the table. Okay, so this here 0 and this cutoff point should be negative here. So you have to check a positive part. Okay, so here also 0, 0, 5. Then all the way down should be 95. So we should check 9500, right? 0.9500. So we find this cutoff point should be 1.64 or 1.65 or 1.645, right? So either one is okay. So suppose, okay, so we find this number should be negative 1.64. So then we can find this cutoff point. So what is this L? So L minus 3.00, so equals this, right? Negative 1.64 times 0075. So L is just equal 3.00 minus this, right? So here just a little bit of calculation, we find there's a cutoff point. So I think it's around 2.87 or 2.88 maybe. So here just a little bit of calculation here, 2.88. Okay, so we say if we use this as a cutoff point, then we can guarantee alpha is not so big. Okay. So here we have the two kind of problem, right? Once we have cutoff point, find probability. So once we have probability, find cutoff point. So such problem actually is from normal table we can do these two things, right? So here we also can regard this as just application for normal table. Okay. Okay. So now let's say. So once we have a cutoff point, we can find alpha. So can we find a beta? So now let's consider this problem. Like we talking about average ACT score. So we know ACT score is high is good. So here we say this is one side. We just only consider one side, right? So some people claim our GPA, our ACT score, average ACT score should be at least 580. So here 580. So but we 580 with standard deviation 100. So this 100 is sigma, right? So this is we say some people say mu at least 580. Okay, so here we're talking about ACT score, so the higher the better. So we only need to check one side. Okay, so we said this as a HO. So we say HO, we have to say HO as equal. Okay, equal. So what is HA? So HA, we can say the larger than or less than. But we say we should set it less than. Less than make more sense. Less than means not so good, right? So larger than is good. So equal. So here we say HO always equal. So HA. So what a good meaning? So what not a good meanings? So here not a good meanings less than. So we said HA as less than. Okay. So now our decision making law is we just give me a cutoff point. So we will check 25 students. We will check 25, and our cutoff point is here is 580. So our cutoff point is here is 576. So we just put this as if we have 4 points difference. We just the 4 point difference as a cutoff point. if difference is more than 4 points, then we say, oh, the difference is big, right? So if less than 4 points, we say, oh, difference is small. So we have this decision-making rule. So we can find alpha. So alpha is just okay. Alpha, so we can easily find alpha. We will reject the HO, so we say if okay. So we say if no, sorry, okay. What's happening? Sorry. Okay, so if here x bar here, we will reject, right? So now, so for find alpha, I leave this for you, so you can do this as a practice. So now, let's check. Can we find beta? So beta is type 2 error. So let's try find beta. The beta is a probability for making type 2 error. So what is type 2? Type 2 is, we say, easily to believe other people. Or we say accept HO when HO is not true. So accept HO means when x bar larger than 576, then we will believe this, right? We will accept their claim. We will believe mu is at least 580 or equal 580. So when HO not true, so when HO not true, so we have to choose. So if HO not true, we have to choose HA. Okay, so we know mu will be less than this. So mu less than this. Mu less than 580. But even though we know mu less than 580, we still don't know mu. So for distribution for x bar, we say x bar follow this normal. Mean, mu, and sigma of radical n. So this mu we don't know. We only know mu mu less than 580. So we say this mu we don't know. So even though we know sigma and n, n we know. N, let's say, n is how many people you will check. We say 25. And what is sigma? Oh, sigma is 100. So here sigma is 100, and n, so this is n is no 25, right? But we don't know mu. So if we don't know mu, then we don't know exact distribution for x bar. Okay, so then for this reason, we cannot find this we cannot find this beta, because we don't know the distribution for x bar. Okay, we don't know exactly distribution. We only know x bar follows some normal distribution, but the mean we don't know. We only know mu is less than 580. So less than 580 can be 570, 520, right? We can have many possible values. Okay, so we say for such a problem, we can only find alpha, but we can find alpha, we cannot find beta. So the reason is why we cannot find alpha, because when HO is true, we know mu, right? So when HA is true, we don't know mu, right? Okay, so if we want to find beta, or find alpha, find beta, we need to know when h is true, we should know what is the exact mu. So only in this case we can find alpha and beta. So we call this case is two points problem, 2-point hypothesis. So here, like HO is for mu, we have only two possible values. Mu equals this number or mu equals that number. Like for example, so here this example is like mu can be 10 and it can be 15. We can only two possible value for mu. So we just need to determine which one. So we set the decision making law, like okay, so here some people say 10, some people say 15. So we wanted to determine. So we just let the data make a decision. So we take a sample. So let's say we will check a sample. So sample size, we will check 25 people, or sample size 25. So what decision making rule is if also cutoff point is 12. Let's see. Okay. So if x bar is less than 12, then HO. We believe mu equals 10. If x bar is larger than 12, then we will believe mu equals 15. Okay? Okay, so for this decision making rule, we try find alpha and find beta. So find alpha, we already did this, those things. Alpha is like a, let's say we will refuse HO when HO is true. So refuse HO. So when we will refuse is when x bar is larger than 12, right? We will refuse. So refuse HO is this. So when HO is true, when mu equal 10. So when mu equal 10, this x bar will follow this normal. Okay, so now we just find this probability. We want to find this probability x bar larger than 12. So such a problem by now become routine. We change this to z. So larger than, so here 12 minus mu over sigma 1.1, right? So we can find this easily. So check a normal table, we can find this. So now let's check a beta. Okay, so beta is type 2 error. So type 2 error is we will accept HO when HO is not true. So we will accept HO. So when we will accept HO, we say less than 12, we will accept HO. So when HO is not true, then we have to pick this. If HO is not true, we just believe HO is true. So if we reject it, if we do not believe mu equal 10, then only choice is mu equal 15, right? So let's say, so this become like when we will accept HO when x bar less than 12, but HO is not true, then HA is true. So when mu equal 15. So such a problem become like, okay, so now the distribution x bar will follow this normal. X bar follow this normal mu sigma over radical n. So here mu is 15, right? Sigma 5.5 n 25. 25, the square root is 5. So we say that in this case the x bar follows this no more distribution. Mean become 15, right? Okay, so by now x bar follow this normal. I'm sorry, x bar follow this normal. Then find this probability x less than 12, x bar less than 12. So we can find this x bar less than 12. So equal p z less than, so here 12 minus mu divided by sigma 1.1, right? So this probability, let's say, is 3 divided by, let's say, negative 3 divided by 1.1, like 2 point, negative 2 point something. I don't know. Let's say. So I need to calculate. But anyway, like you can find. So there's a probability. So we can easily find this probability. I think this probability is quite small. Okay. Okay. So let's say. So here we say. So this in this example, we can find alpha is small or beta is also small. So this means use this decision making rule, we almost will not make any mistake. We will have a very small chance to make a type 1 error or very small chance to make a type 2 error. So this is good. So actually for this simple case, is we wanted to just separate 10 or 15, or this we say this is easy. We just use this way. We can separate them easily, and we will not make much mistake. Okay. Okay, so we say alpha and beta is probability for making mistakes. Okay, so we hope this alpha and beta, both of them are quite small. The smaller the better, right? But how about if can we set this alpha and beta as 0? So we say if we cannot expect those alpha and beta as 0, because if the alpha and beta is 0, means we will make no mistake. So if we want to guarantee we will make no mistake, then almost we cannot make any decision, right? Okay, so we say we cannot expect to make we cannot expect that alpha and beta will equal 0, but we can hope those are quite small. Okay, so we finish today's topic. So we say that today's topic is type 1, type 2 error. Okay. So we say once we have a decision making rule, once we have a cutoff point, then we can check with this decision making rule. We can find alpha, but for beta, usually we can only find beta for this typical situation, 2 points testing, right? So possible value for this mu is only have 2 possible values, so either this one or that one. So we determine which one is more likely. So just use the cutoff point, right? Okay, so this is the last topic for this exam 2. So next Monday we will have exam 2. Okay. Okay. So we can stop here, and thank you for watching. And I'm sorry for any inconvenience. Okay, so we can stop here and bye bye. See you in class. Okay, bye.